Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it.
This is chapter 3.4, which is on exponential and logarithmic equations. So in here, we're going to discuss how to solve exponential and logarithmic equations. But first, let's recall two things. Recall the one-to-one properties, which are that if I have a to the x is equal to a to the y, if and only if x is equal to y. All right, that was the first of the two one-to-one properties. The other one was that if I have log base a of x is equal to log base a of y, then this tells us also that x equals y. Similarly, we've got the inverse properties, right? And the inverse properties, where the exponential was that if I had a to the log base a of x, I get x, and log base a of a to the x is equal to x. All right, now we're going to be using those two properties a lot, as well as the log properties. So the log properties were that if I had log base a of m times n, I get log base a of m plus log base a of n. If I had log base a of m over n, we end up with log base a of m minus log base a of n. And finally, if I have log base a of m to the r, I end up with r log base a of m. All right, so these properties, the one-to-one as well as the inverse, as well as the properties of logs, are going to help us solve a bunch of these equations. So let's start easy, and then we'll slowly come up with harder examples. So solve. And here we've got, well, something like 2 to the x is equal to 32. We already know how to solve this, right? In here, what we need to do is write 32 as a power of 2. In other words, we can have 2 to the x is equal to 2 to the 5th, meaning that x is equal to 5. All right? That one wasn't bad at all. Let's do another one. If I have ln of x minus ln of 3 is equal to 0, well, there's two ways I can solve this. The first way, I can say that if I move this ln of 3 to the other side, I've got ln of x is equal to ln of 3, therefore x is equal to 3. The other way that I can solve this is using rules of logs. So I'll do the second version here in blue. And since I have this minus here, I can use the quotient property, or the quotient rule for logs, and rewrite it as ln of x over 3 is equal to 0. Then exponentiate both sides with base e. On the right side, e to the 0 is 1. On the left side, e to the ln of x over 3. Well, these cancel each other out, so I end up with x over 3. Multiply both sides by 3, x equals 3. So in both of these scenarios, we get the same answer as we should. They're just two different ways of solving the same equation. Next one. All right, so let's see. If I had something like 1/3 to the x is equal to 9, well, here, simply the left side can be written as 3 to the negative x. The right side can be written as 3 squared. So therefore, negative x is equal to 2, which tells us that x is equal to negative 2. Right? Cool. Now, let's kick it up a small notch. If I have something like 5 minus e to the x is equal to 0. And here, the first thing I'm going to do is move the e to the x on the other side. So I have 5 is equal to e to the x. And then I'm going to take the log of both sides. So I'm going to say ln of 5 is equal to ln of e to the x. On the right side, ln of e to the x, the ln and the e cancel out, and we just end up with x, right? On the left side, I'm just going to leave it as ln of 5. And that's our answer, all right? X equals ln of 5. Now, as far as what that value is, doesn't matter. It's ln of 5, all right? You can plug it into the calculator, and you would say here, so you would see that ln of 5 is approximately 1.60944. All right, that's just rounded off. But the real answer here is just ln of 5. X equals ln of 5. Perhaps I'll circle the bottom one. This one. All right. So again, this one wasn't too bad. All we did was apply one extra rule. And similarly, if I have ln of x is equal to something like -7, well, I can just exponentiate both sides, and we have e to the ln of x is equal to e to the -7. At that point on the left side, the e and the ln cancel out, so I have x is equal to just e to the -7. And that would be our final answer, all right? Now, I know that in general, we like to write our final answers without negative exponents, but with e is one of the few exceptions, all right? We don't mind e written as our final answer with a negative exponent. If you really wanted to, you can just write it as 1 over e to the 7th, but e to the -7 is acceptable. Next one. So if I had something like log of x is equal to -3, all right? In here, recall that when I just write log, there's an invisible base 10 there, all right? So to get rid of this, well, we need to exponentiate with the base. So 10 to the log of 10 to the log of x is equal to 10 to the -3. There we go. At that point, the 10 and the log cancel each other out, and I just have x is equal to 10 to the -3, which is 1 over 1,000, right? 10 to the 3rd is 1,000. So that would be our final answer. Next one. We're going to go through a lot of these. If I had a different base, something like log base 3 over x is equal to 4, right? Well, same exact trick that we just did. We just need to exponentiate with our base. Our base is 3, so I'm going to say that we get now 3 to the log base 3 of x is equal to 4. So we can just simply say it's equal to 3 to the 4th. So simply, x is equal to 3 to the 4th, which is 81. All right. Now, you may be wondering, do you have to write every single step like this? Not necessarily. You could have just kind of said, well, from here, by exponentiating both sides, I know that the 3 and the log 3 are going to cancel out. So you can just say x is equal to 3 to the 4th, which is how we get x is equal to 81. All right. You should write this middle step, though, that 3 to the 4th. Anyway, next one, h. Let's take it up another notch. So if I have e to the 2x is equal to e to the x squared minus 8, well, simply, we already have them both on the same base, so we end up with just 2x is equal to x squared minus 8, putting everything on the same side. X squared minus 2x minus 8 is equal to 0. Factoring x plus 4 times x minus 2 is equal to 0, which tells us that x equals -4 or x equals +2. All right. And in here, well, we know that with exponentials, the domain is always all real numbers, so both of these work just fine. Next one. Let's say that I had something like 3 times 2 to the x is equal to 42, right? the very first thing I'm going to do here is divide both sides by 3. So I have 2 to the x is equal to 42 divided by 3 is 14. Now, in here, this 14 cannot be written as a base 2, right? So what I'm going to do here is we could take log base 2 of both sides to get rid of this 2, but I'm going to advise you to start using ln for everything, all right? So what I'm going to do here is I'm going to take the natural log of both sides, giving me here that x is equal to, sorry, let me just rewrite this. In here, I could bring the x to the front, right? So I have x ln of 2 is equal to ln of 14. So finally, x is equal to ln of 14 to ln of 2, which is equivalent to what we would have gotten if we had done things with base 2. What do I mean? So we had 2 to the x is equal to 14 at this point, right? So if I had done things with base 2, so log base 2 of 2 to the x, that would give us log base 2 of 14. On the left side, the log base 2 and the 2 cancel out, so we have just x. On the right side, we have log base 2 of 14. Now, these two answers are equivalent. How come? Well, using the change of base formula to make it base n, this would just give us ln of 14 over ln of 2, as is written over here. And if you don't recall it, I'll just write down real quick what the change of base formula was. Log base a of b, if I'm going to go to ln, would be ln of b over ln of a, which is exactly what I did here. All right. All right. Next one. So that was I. J. Let's say I had e to the x minus 7 is equal to 23. So again, the very first thing I'm going to do is, well, put any non-x's to the same side. So I have e to the x is equal to, well, add 7 to both sides. So it's equal to 30, right? And at that point, take ln of both sides. So on the left side, I'm going to have just x. On the right side, I have ln of 30, all right? And notice I didn't write the step of actually taking ln of e to the x, because I know that ln and e are just going to cancel out and leave us alone with just that x. All right. Next one. Okay. Let's say I have 3 times log base 4 of 6x is equal to 9. Well, very first thing I'm going to do is get rid of this 3. So I have log base 4 of 6x is equal to 3, right? Divide both sides by 3. Then exponentiate both sides to get rid of this log base 4. I'm just going to write it as 6x is equal to 4 to the third, right? And again, notice I didn't actually write the step of writing 4 to the log base 4 because I know they're going to cancel out. So finally here, divide both sides by 6. So x is equal to 4 to the third, which is 64, divided by 6. These are both divisible by 2. So I end up with 32 over 3. Now, next one. L. So if I had something like log of x minus log of x minus 9 is equal to 1. All right. So in here, the very first thing I'm going to do is I'm going to combine these two, right? So I'm going to say this is really just saying log of x over x minus 9 is equal to 1. This is just applying the rules of logs, right? Next thing, I'm going to exponentiate both sides with base 10, right? Because that's how we get rid of log. But I'm just going to write it as x over x minus 9 is equal to 10 to the 1. Now 10 to the 1 is just 10. Move the x minus 9 to the other side, so I have x is equal to 10 times x minus 9, which simplifies to be 10x minus 90. At that point, put all the x's on the same side and all the non-x's on the other. So I'm going to have 9x is equal to 90. All right, so essentially move this x over here, move this 90 on this side, and then switch the order. And that gives us simply that x is equal to 10. All right, now that would be our final answer here. M. So if I had something like ln of 5x plus ln of x minus 1 is equal to 2 ln of 10. Well, again, I'm going to start with the same exact thing. With equations like these, when we have a bunch of ln's, what you want to make sure is that you have at most one ln on each side. What do I mean? Well, on the left side, I can rewrite it as the ln of 5x times x minus 1. On the right side, I can write it as ln of 10 squared. All right. So on the left side, I just use the rules of the product rule for logs. On the right side, I use the power rule for logs. So what does that tell us? Well, the insides must be equal to the same thing because of the one-to-one property. So if I distribute this 5x, I end up with 5x squared minus 5x. On this side, I got 100. So essentially, I got rid of the ln's. I see everything here is divisible by 5. So I'm going to divide everything by 5. So I have x squared minus, I said I divided by 5. X squared minus x is equal to 20, which at that point, we would say, though, this is really just saying x squared minus x minus 20 is equal to 0. Factor out the left side, so that's x minus 5 times x plus 4 equals 0. So either x is equal to 5 or x is equal to negative 4. Now, here we have a situation that we had not encountered before. All right. And the situation is that, well, we really need to consider what the domain of this problem is. Because from the very beginning here, this part, 5x, must be greater than 0, which tells us that x must be greater than 0. Here, x minus 1 must be greater than 0, so x must be greater than 1. So what we need to do is look at our answers and see which of these fit both, which are both greater than 0 and greater than 1. Well, it turns out that x equals 5 is the only solution, right? Because 5 is the only one that's both greater than 0 and greater than 1. So x equals 5 is a solution, negative 4 is not. This would be called an extraneous solution. All right. So you have to be sure to test for the domain of these kinds of problems. This had not been an issue before, and let me show you why that was why that's the case. All right. So in here, in the previous example, here, x had to be greater than 0 and x had to be greater than 9. Our answer of 10 is both, so there's nothing wrong with that. In this one, here, x had to be greater than 0. Our final answer, 32 over 3, a positive number, definitely greater than 0, all right? And that's true for all the previous examples where we had an ln equation, all right? So you have to make sure that you look for the domain. All right, so let's take it up a notch with more exponentials and more logarithmics. So that was M. N. All right, so if I had something like 2 to the 8x minus 4 times 16 to the 3x minus 5 is equal to 16 to the 9x plus 2. All right. So in here, the very first thing I'm going to do is put everything to the same base. All right. 16 can be written as base 2 in the following manner. So 16 is just 2 to the 4th. And we have that raised to 3x minus 5. And here again, we have 2 to the 4th raised to the 9x plus 2. And that 4 is an exponent. So from rules of exponents, we can rewrite this as follows. This 2 to the 4th, well, this 4 can be multiplied to this exponent. Same thing for this one. right? That's just from rules of exponents. And now that we have everything base 2, well, let's do one last thing on the left side. We know that when we have the same base, different exponents, we can just add up the exponents. So I have 8x minus 4 plus this statement, but I'm going to distribute. So 12x minus 20 is equal to 2 to the, if I distribute this 4 times 9 is 36, and then plus 8. At that point, what can we do here? Well, we can say that the exponents must be equal to each other. So we have 8x plus 12x, so 20x, and negative 4 plus negative 20 is negative 24, must be equal to 36x plus 8. All right. At this point, let's put all the x's to one side and all the non-x's to the other. So I end up with negative 16x is equal to 32. Right, so I just added 24 and subtracted 36 on both sides. So that tells me that x is equal to negative 2. In an exponential equation, you don't need to worry about the domain because the domain for exponentials is always all real numbers. So as long as you get a real number, you don't have to worry anything about it. Let's do another one kind of like this. All right, so that was n. Oh, let's say that I had 5 to the 6x plus 5 over 125 to the 3x minus 1 is equal to 5 to the negative 5x plus 2. All right, so in here, there's a couple of different ways that we can do this. The very first thing I'm going to do here is, well, you should recognize that 125 is 5 to the third. So I really have 5 to the 6x plus 5 over 5 to the third to the 3x minus 1, and that was a 5. There we go. Equals 5 to the negative 5x plus 2. And again, from rules of exponents, I could rewrite the left side as 5 to the 6x plus 5 over 5 to the 9x minus 3 is equal to negative 5x plus 2. Finally, my last thing for setup here, hold on, that was supposed to be 5 to the negative 5x plus 2. 5 to the negative 5x plus 2. There we go. Finally, on the left side, using rules of exponents, I can rewrite it as 5 to the negative 3x plus 8, right? Because I'm subtracting the exponents. 6x minus 9x is negative 3x. 5 minus negative 3 is positive 8. Same base, different exponents. Divide, subtract exponents. All right. And this is equal to 5 to the negative 5x plus 2, telling me that negative 3x plus 8 is equal to negative 5x plus 2. Putting all the x's on the same side, I get 2x is equal to negative 3, right? So I added 5 to both sides, subtracted 8 from both sides. Therefore, x is equal to negative 3/2. And of course, I made a mistake. Where did this 5 come from? It was a 2. So let's fix that. So this was supposed to be a 2. And if I move the 8 over to that side, right, subtract 8 from both sides, I get negative 6. And now dividing both sides by 2, I get negative 3. There we go. Now it's correct. Cool. And again, we don't have to worry about the exponents because in exponential functions, the domain is all real numbers. So that was O. P. Let's kick it up a notch. Let's say that I have e to the 8 minus 3x is equal to 268. All right. So in here, the very first thing I'm going to do is take ln of both sides. So I have 8 minus 3x is equal to ln of 268. All right. So now subtract 8 from both sides. So I get negative 3 is equal to ln of 268 minus 8. Divide by negative 3. X is equal to ln of 268 minus 8 over negative 3, which can be written as 8 minus ln of 268 over positive 3. So I just brought the negative to the top. But that would be our final answer. All right. There's no need to try to simplify this any further because it doesn't. All right. Cool. So that was P. Q. Let's do something similar to this one. So if I had something like 3 to the 6x plus 7 is equal to 761. Well, the very first thing I'm going to do here is take ln of both sides. So I'm going to write it as, I'll write it all out. ln of 3 to the 6x plus 7 is equal to ln of 761, which tells me that 6x plus 7 times ln of 3 is equal to ln of 761. Dividing both sides by ln of 3, 6x plus 7 is equal to ln of 61 over ln of 3. Subtract 7, divide by 6. So, well, let's subtract 7 first. So I'm going to say 6x is equal to ln of 761 over ln of 3, which finally tells me that x is equal to, oh, hold on. What happened to subtracting 7? Minus 7. There we go. Which tells us that if I divide both sides by 6, I end up with x is equal to ln of 761 over 6 ln of 3 minus 7/6, right? Because I divided both sides there by 6. All right. So that was Q. And again, notice I'm leaving my answers like this and just in terms of ln. All right. You shouldn't try to get a decimal answer for these, just unless it was a word problem. But in general, we liked exact form. This is called exact form. All right. All right. So that was Q. R. I'll do one more like this, I guess. If I had something like 5 to the 2x minus 5 is equal to 87. Well, in here, I'm going to say that if I take ln of both sides, so I'm going to write it as 2x minus 5 times ln of 5 is equal to ln of 87. Notice that I skipped a step because I knew I wasn't able to bring the exponent down to the front. Divide both sides by ln of 5, so 2x minus 5 is equal to ln of 87 over ln of 5. Add 5 to both sides, 2x is equal to ln of 87 over ln of 5 plus 5, which tells us our final answer is just x is equal to ln of 87 over 2 ln of 5 plus 5 halves. All right. Next one. Let's pick it up a notch. So that was R. S. Let's say I have 2 plus log of the square root of 1 plus x plus 3 halves times log of 1 minus x equaling 1/2 of log of 1 minus x squared. All right. So in here, the very first thing we're going to do is put all the logs on one side and all the non-logs on the other side. All right. So anything that has a log, put it together on one side, and anything that doesn't have a log, put it on the other side. At the same time, I'm gonna change like this square root to a fractional exponent, and I'm gonna use the power rule. Well, actually, you know what? I'll do it in 2 steps. So let's do all the logs on one side. So 1 minus x minus 1/2 of log 1 minus x squared, and then move the 2 to the side, so -2. All right, so I move this piece to the left, this piece to the right. Next thing I'm going to do is I'm going to write this as just one logarithmic statement on the left side. So what do I mean? I'm going to have log of, in here, the square root of 1 plus x is really just 1 plus x to the 1/2. And then remember, when we're adding, is going to be a multiplication on the top. When we're subtracting, it's going to be a division on the bottom. So in here, I'm going to have this 1 minus x to the 3/2, and then over 1 minus x squared to the 1/2 is equal to -2. Now, at this point, what we can do is get rid of this log, right? Exponentiate both sides with base 10. So I'm just going to have the inside stuff, 1 plus x to the 1/2 times 1 minus x to the 3/2 over 1 minus x squared to the 1/2 is equal to 10 to the -2. At that point, well, let's see how we can cancel some stuff out here. In here, this 1 minus x squared to the 1/2, I can rewrite this as 1 plus x to the 1/2 times 1 minus x to the 1/2. I'm essentially using the difference of squares here and distributing the exponent to each piece. All right, so I apply the difference of squares to factor into the product of conjugates and apply that exponent, that's a 2 by the way, and apply that exponent to both pieces. So we're no longer looking at it this way in the bottom. How is that helpful? Well, we see here that the 1 plus x to the 1/2 over 1 plus x to the 1/2, those are going to cancel out. Over here, 1 minus x to the 3/2 over 1 minus x to the 1/2, that's just simply going to reduce to be 1 minus x to the 1, right? 3/2 minus 1/2 is just 2/2, which is 1. So I have 1 minus x is equal to 1 over 100. At that point, well, subtract 1 from both sides. So I get negative x is equal to 1 over 100 minus 1. And then divide by negative. So x is equal to 1 minus 1 over 100. But 1 minus 1 over 100, well, 1 is 100 over 100. So 100 over 100 minus 1 over 100 is 99 over 100. Now, in here, we did start with logarithmic statements. So we really should check our solutions, our domain here. From this first one, we have to have that 1 plus x. So here the domain of the problem is, well, 1 plus x must be greater than 0 from here. So in other words, x must be greater than -1. But then from this one over here, we have 1 minus x must be greater than 0. So therefore, x must be less than 1. All right. All I did was move the x to the other side. So we have to be greater than -1 and less than +1. So we're between here and here. So it must be some value between there. Well, our answer of 99 over 100 is definitely less than 1, right? Because the numerator is smaller than the denominator, tells us our fraction is smaller than 1. So, by the way, notice I didn't have to check this one over here. I didn't have to check this one over here because essentially it would have been taken care of by these two, because this 1 minus x squared is a product of 1 plus x times 1 minus x. So since I checked those already, we don't need to worry about anything else. All right, so that's S. Let's do another one like this that has a bunch of logs. So ST. Let's say that I have log base 8 of x plus log base 8 of x plus 6 is equal to log base 8 of 5x plus 2. And the very first thing I'm going to do is apply the rules of logs to just have at most one log on each side. So on the left side, I'm going to write it as log base 8 of x times x plus 6. The right side, leave it alone. This tells me now that the insides must be equal to each other because we have the same log with the same base. So in here, I'm going to write it as x squared plus 6x is equal to 5x plus 2. I don't know where I got that 6 from. 5x plus 2. Put everything on the same side. X squared plus x minus 2 is equal to 0. So therefore, I have x plus 2 times x minus 1 equals 0. So either x is equal to -2 or x is equal to 1. But this problem came from a logarithmic statement, right? We had a whole bunch of logarithmic statements here, so we have to check our domain. So from this first one, we get, so the domain for the problem, x must be greater than 0. From here, x must be greater than negative 6. And from here, x must be greater than negative 2/5. So when we have a whole bunch of statements like these, what you really want to do is take a look at which one's the most restrictive. X being greater than 0 is the most restrictive. What do I mean by that? Well, if I put all these on the number line, right? And I'm going to put them all on the same number line. So let's see. Here's 0. Here's negative 2/5. Here's negative 6. X being greater than 0 starts here and moves that way. X being greater than negative 6 starts here, moves that way. And lastly, x being greater than negative 2/5 starts here, moves that way. So when I say which one's the most restrictive one, I'm talking about, well, which one has less, quote unquote, less values. Well, this piece right here would be the least values, right? Because you can't include negative values in the first one, and you can't include things like -1, -2, -3 in this third one. So the most restrictive would be this one, the one that's the smallest in these number lines, this one right here. Another way to think about it is, whichever one, all of them are overlapping, is the answer, or the domain. So we must have that x is greater than 0, since that's our most restricting answer, or restricting domain. So our answer must be x is greater than 1, and this right here will be an extraneous solution. That's just extraneous. All right. I'll write it better. Oh yeah, way better. Extraneous solution. All right. So that was T. U. Let's say that I have log base 3 of x squared. No, what? Log base 3 of x plus log base 3 of x minus 6 is equal to 3. So in here, very first thing, combine the logs, right? We want to have at most just one log on each side. So in here, I'm going to write it as log base 3 of x times x minus 6 is equal to 3. Exponentiate both sides with this base 3. So I have x times x minus 6 is equal to 3 to the third. Expand the left side. X squared minus 6x. 3 to the third is 27. I'm going to move that to the other side as well at the same time. So I have x squared minus 6x minus 27 is equal to 0. That factors out to be x minus 9 times x plus 3, which tells us that either x is equal to 9 or x is equal to negative 3. But from the beginning, we had that the domain here, x had to be either greater than 0 or x had to be greater than 6. Which is the more restrictive one? X being greater than 6, right? Because in here, you're allowed to have things like 1, 2, 3, 4, 5. You're not allowed to have those here. So the one that's most restrictive is the real domain. So in here, this tells us now that x equals 9 is our actual solution. And this right here would be an extraneous solution. All right. So that was extraneous. Extraneous solution. All right, so that was U. V. Let's say that I have log of x minus 2 minus log of 2x minus 3 is equal to log of 2. So in here, combine the logs, so I end up with log of x minus 2 over 2x minus 3 is equal to just log of 2, giving me that x minus 2 over 2x minus 3 must be equal to just 2. Multiply both sides by 2x minus 3, so x minus 2 is equal to 4x minus 6, right? I just distributed. 2x times 2 is 4x, negative 3 times 2 is negative 6. Put all the x's on the same side, all the non-x's on the other side, so I end up with 3x is equal to, so I did move the x that way, 3x, move the negative 6 this way, so it's plus 6, so I end up with 4. Therefore, x is equal to 4/3. But now, let's check the domain of the problem. From the beginning, the domain is this x minus 2 must be greater than 0, so x must be greater than 2. Here, 2x minus 3 must be greater than 0, so x must be greater than 3/2. Now, is this actually within our domain? Well, 3/2, well, actually, let's look at this. 3/2, we know that this is 1.5, right? So between these two, x being greater than 2 is the most restrictive. 4/3, however, is approximately 1.3. Well, it's actually equal to. It's exactly equal to 1.3 with the 3 repeating, right? Now that would not be bigger than 2. It also wouldn't even be bigger than 1.5, right? So what does that mean? Well, that means that here this has no solution, because this right here is an extraneous solution. And the extraneous solution was our only possible answer here, and therefore no solution. All right, so it's important to check for these. All right, and you can very clearly see why you wouldn't be able to plug this in, right? If I plug in 4/3 here, 4/3 minus 2, that's a negative value. 2 times 4/3 is 8/3. 8/3 minus 3, that's also a negative value. So from the very beginning, that 4/3 is not even allowed, all right? Because you get negative values inside the logs here. All right, so that's B. W. So W, we get, let's have something like log base 4 of 3x minus 2 minus log base 4 of 4x plus 1 is equal to 2. All right, so once again, let's do the rules of logs. The quotient rule. So I have log base 4 of 3x minus 2 over 4x plus 1 is equal to 2. Exponentiate both sides with base 4, so I end up with 3x minus 2 is equal to 4x plus 1 is equal to 4 squared. Now 4 squared is simply just 16. So if I multiply this thing up here, well, I end up with 3x minus 2 is equal to 4x times 16 is 64x. 1 times 16 is 16. Put all the x's on the same side, all the non-x's on the other side. So 3x, so 64 minus 3 is 61. So I move this 3x to the right, move the 16 to the other side. So I'm subtracting 16, which is how I get negative 18. Therefore, x would just simply be negative 18 over 61. But let's look at the domain of the problem. From the first part, we had that x must be greater than 2/3, right? Because 3x minus 2 must be greater than 0. From the second part, we have that x must be greater than negative 1/4. In here, this negative 1/4 and this 2/3, well, from these two, 2/3 is the more restrictive one, right? So in here, this negative 18 over 64 doesn't work, all right? It doesn't work. So what we get here is no solution, all right? There's no solution for this. All right, let's switch gears a little bit. So that was W. x. And I guess we could get up a small notch as well. Let's say that we had something like log base 4 times log base 3, not times, log base 4 of log base 3 of log base 2 of x. And that's going to be equal to 1/2. All right, well, let's look at this problem one step at a time. In here, what we really have is log base 4 of something is equal to 1/2. How do we solve log base 4 of something equal to 1/2? Well, we exponentiate both sides with base 4. So what I'm going to say here is, well, on the left side, I'm just going to have log base 3 of log base 2 of x is equal to 4 to the 1/2. But 4 to the 1/2 is just the square root of 4, so it's really just 2. All right. Next thing. You know what? I'll write that in a different color. So it's equal to just 2. There we go. Next thing. Get rid of this log base 3. And in here, well, again, similar idea. What do we really have here? We have log base 3 of something is equal to 2. Well, what does that mean? Well, we need to exponentiate with both sides with base 3. So on the left side, I'm just going to write it as log base 2 of x. On the right side, I write it as 3 squared. But 3 squared is just simply 9. All right, cool. Lastly, we have log base 2 of x. So exponentiate with base 2. So I end up with x is equal to 2 to the 9th. But 2 to the 9th is just simply 512. All right. And there's nothing wrong with 512 because inside here, we needed to make sure that x is greater than 0, right? That's the domain of this problem. 512 is definitely greater than 0. So that's our final answer. All right. Y. Let's say that I have 3 log 2 minus log of x minus 1 is equal to log of x plus 1 minus log of x minus 2. And, well, the very first thing I'm going to do here is write this all as, well, write each side as just one logarithmic statement, all right? We want to make sure that we have no more than one logarithmic statement on each side. So on the left side, I'm going to have log of, well, bring this 3 to the exponent here, right from the power rule. So log of 8 over x minus 1. This x minus 1 is on bottom from the quotient rule. Is equal to log of x plus 1 over x minus 2. At that point, I've just got log on both sides. So I can ignore the logs and set the insides equal to each other, which gives me now, well, x minus 2, so I'm going to cross multiply. So x minus 2 times 8 is 8x minus 16. X minus 1 times x plus 1, well, that's the difference of squares, right? Because I've got the product of conjugates. The product of conjugates is the difference of squares. Putting everything on the same side now, what I get is that x squared minus 8x plus 15 is equal to 0. And this factors out to be x plus 5 times x plus, excuse me, not x plus 5, x minus 5 times x minus 3 is equal to 0, which gives me that either x is equal to 5 or x is equal to 3. We need to check the domain of this problem though. So perhaps I'll shift some of this up here so we can see the domain. All right, so in here, the domain for the problem, this x minus 1 has to be greater than 0, so that means that x has to be greater than 1. This x plus 1 has to be greater than 0, so that means that x has to be greater than negative 1. And this x minus 2 has to be greater than 0, so that means that x must be greater than 2. The most restrictive is that last one. So x must be greater than 2. Well, they both work. They both work. So we get two solutions, 5 and 3. Next one. So that was y. Z. Let's say that I have log base 3 of 1 minus x is equal to log base 3 of x. Let's do it this way. Log base 3 of negative x squared plus 16. What? No, plus x plus 16. All right. Now, in here, well, I already have it just one log on each side, right? So right away, this tells me that 1 minus x must be equal to negative x squared plus x plus 16. Putting everything on the same side, so I'm going to move everything from the right side to the left. I'm going to have x squared minus 15, excuse me, x squared minus 2x minus 15, right? So move the x to this side, so x squared minus 2x minus 15 is equal to 0, giving me that this factors out to be x plus 3 times x minus 5. So our final answer here is either x is equal to negative 3 or x is equal to 5. But from our domain here, let's look at our domain. This part, 1 minus x, has to be greater than 0. So that gives us that x must be less than 1. All right. And remember, we have 1 minus x is greater than 0. So that's how I get x is less than 1. From the second one, though, that's a little more difficult. Let's see. So we have that negative x squared plus x plus 16 must be greater than 0. Well, if you recall about our quadratic inequalities, we have to treat it as an equal sign and then test around it. So I'm going to write this as negative x squared plus x plus 16 is equal to 0. Divide everything by negative 1. X squared minus x minus 16 has to equal to 0. Factor. Well, this is not factorable. There's something that multiplies to both 16 and adds up to 1, right? 16 is either 1 times 16, 2 times 8, or 4 times 4. And none of those additions would give me that negative 1. Now, at this point, we would need to use the quadratic formula. But since this lecture is not about these inequalities in here, I'm just going to tell you what we essentially get. We essentially get x is equal to 1 plus or minus radical 65 over 2, which gives me the two solutions of approximately, let's do it this way, approximately the positive version, the one we do with the plus, is approximately positive 4.5, and the negative version, the one we do with the minus, 1 minus radical 65 over 2 is approximately negative 3.5. So we would test around those. And again, I'm not gonna do it in detail here, but essentially we end up that this region is false, this region is true, this region is false. So we have to have something in between here. Now, we must be less than 1 and somewhere between negative 3.5 and 4.5. All right, we have to apply both of these. So right away, that tells us our answer must be negative 3, and x equals 5 would be an extraneous solution. All right, because again, we have to be both less than 1 and between these values. Negative 3 is the only one from these options that does both of these. All right, so that was Z. So that was the alphabet. Let's do another one. A. Right, this is technically A2, I guess. I don't know. But I just write it as A. So if I have something like log of x over log of x plus 1 is equal to negative 1. Well, this gives us, if I multiply log of x plus 1 to this side, and that with log of x has to be equal to negative log of x plus 1. Add this log to this side, I end up with 2 log of x is equal to 1. divide both sides by 2. Log of x is equal to 1/2. Therefore, x is equal to 10 to the 1/2, or sorry, where did this positive 1 come from? It's negative, right? Because negative 1 times positive 1 is negative, negative, negative. There we go. So my final answer here is 1 over the square root of 10, right? Which we can rewrite it as radical 10 over 10. And is that okay? Well, from the very beginning, the domain of this problem, well, we had to have x had to be greater than 0 from this part and this part. But also here we have a fraction, so that means that log of x plus 1 cannot be equal to 0, giving me that log of x cannot be equal to negative 1, giving me that x cannot be equal to 10 to the negative 1, which is 1/10. So x has to be greater than 0 and not equal to 1/10. Well, 1 over radical 10 is not 1/10, so that's our solution. So we're good. There is no issue. All right. Now, B. Let's say that we had, so we're kicking it up a notch. Log base 2 of 9 minus 2 to the x over 3 minus x is equal to 1. Here we go. The very first thing I'm going to do here is I'm going to multiply both sides by 3 minus x. When I multiply both sides by 3 minus x, I end up with log base 2 of 9 minus 2 to the x is equal to 3 minus x. Next thing, I need to exponentiate to get rid of this log base 2. And how do we exponentiate? Well, the left side is simple. It's just 9 minus 2 to the x. The right side, though, is going to be 2 to the 3 minus x. So essentially what I'm getting at here is when I have something like log base a of b is equal to c, I can rewrite this as b is equal to a to the c, right? These two statements are equivalent. This is just the exponential form. Well, that's exactly what happened here. This is our a, this is our b, this is our c. So we have b is equal to a to the b. Excuse me, a to the c. All right, let's continue to solve this though. How do we solve this? Well, here on the right side, I'm going to use rules of exponents. So let's look at if I have 2 to the 3 minus x, that can be written as 2 to the third over 2 to the x. Not negative x, just 2 to the x. Right? So in other words, that's just essentially 8 over 2 to the x. So let's write that. So I have 9 minus 2 to the x is equal to 8 over 2 to the x. I'm going to multiply both sides by 2 to the x. So I have now 9 times 2 to the x minus 2 to the x squared is equal to 8. Again, I just multiply both sides by 2 to the x. Putting everything on the same side, and I'm going to move everything to the right side. So I'm going to have 0 is equal to 2 to the x squared minus 9 times 2 to the x plus 8. Right? And that's equal to 0. And at this point, I want you to notice something. This is in the form of a quadratic function or a quadratic equation, right? It's something like x squared minus 9x plus 8. But we can't use x. So what I'm going to say here is we're going to make a u substitution. We're going to say let u be equal to 2 to the x. So this is going to be now just simply u squared minus 9u plus 8 is equal to 0. This factors out to be u minus 8 times u minus 1, which gives us that either u is equal to 8 or u is equal to 1. But from there, well, what was the problem about? The problem was not about you, all right? The problem is never about you. The problem is always about your x. So you have to make sure that you put things back in terms of x. So what we're going to say here is 2 to the x is equal to 8. 2 to the x is equal to 1. On the left side, x is equal to 3. On the right side, x is equal to 0, right? Because 2 to the third is 8, and 2 to the 0 is 1. Now, let's look at the original problem. We need to have from the very beginning, this inside stuff, 9 minus 2 to the x, must be greater than 0. So let's look at the domain of the problem. So we had, I'll write it here. The domain was that 9 minus 2 to the x must be greater than 0. So therefore, 2 to the x must be less than 9. So therefore, x must be less than log base 2 of 9. Now, log base 2 of 9 is approximately, well, if we use the change of base formula, we can plug it into the calculator as ln of 9 divided by ln of 2, which gives us approximately 3.169. 925. There we go. So our x value must be less than that. But what else? From here, we know that when we have a fraction, the denominator cannot be equal to 0. So we also have to have that x cannot be equal to 3. So x has to be less than 3.16 or so, and not equal to 3. Well, x is equal to 3 here, so it cannot be that. So our only solution there is x equals 0, making x equals 3 an extraneous solution. All right, so that was B. C. Let's kick it up another notch. Let's say that we have log base 3 of 1 plus log base 3, and that's a 3, log base 3 of 2 to the x minus 7 is equal to 1. So, well, how do we solve this? Well, overall, we had log of something is equal to 1. How do we get rid of that? By exponentiating. So I do 3 to the powers on each side. So I'm going to have it as 1 plus log base 3 of 2 to the x minus 7 is equal to 3, right? 3 to the 1 is just 3. Move the 1 over. So I have log base 3 of 2 to the x minus 7 is equal to 2. Exponentiate again. So in other words, 3 as a base on both sides, giving me simply that 2 to the x minus 7 is equal to 9, right? 3 squared is 9. Add 7 to both sides, so I end up with 2 to the x is equal to 16, giving me simply that x equals 4, right? Because we already know that 2 to the 4th is 16. Remember, this is saying 2 to some power equals 16. Well, that power is 4. All right. And is that an okay solution? Well, yeah. Really, the only part that we have to check is this part right here, right? And in here, this is saying that 2 to the x minus 7 must be greater than 0. So 2 to the x must be greater than 8. Well, must be greater than 7. Right? And if I take it on both sides, or excuse me, if I take log base 2 of both sides, or use the apply the change the base formula for ln's, I end up with approximately 2.8. Right? Which makes sense, right? Because we know that 2 to the 3rd is 8. So it should be a very close answer. So we have that x must be greater than 2.8, which is good. All right. And I should have done all this in yellow. All right. So that was C. D. Let's say that I have log base 5 minus x, all right, so that 5 minus x is in the base, of x squared minus 2x plus 65 is equal to 2. So the very first thing I'm going to do here is exponentiate both sides, because I want to get rid of that log. But to what base? Well, the base that I'm going to exponentiate both sides to is just going to be 5 minus x. All right. On the left side, the 5 minus x and the log of 5 minus x, they cancel out. So we end up with just simply x squared minus 2x plus 65. On the right side, we end up with 5 minus x quantity squared, all right, because we're exponentiating there. So at that point, we're going to say, well, the right side, let's expand it. This gives us 5 squared minus 10x plus x squared. But 5 squared is just simply 25. And on this side, we've got x squared minus 2x plus 65. Moving everything to the same side, we'll subtract x from both sides. Subtract x squared from both sides. That goes away. Add 10x to both sides. I end up with 8x. And actually, I'm going to subtract 65 from both sides. I end up with negative 40. So that x is equal to negative 5. All right. And there's nothing wrong with that number, right? Even if you didn't want to. So in this case, I'm not going to look for the actual domain. I'm just going to see if plugging this negative 5 makes sense. So in here, 5 minus negative 5 gives us positive 10. You're allowed to have a positive 10 as a base, so that's fine. Plug in negative 5 into here. Negative 5 squared, 25. 2 times negative 5, negative 10, but we're subtracting, so it's positive 10. So we have 25 plus 10 plus 65. Overall, that's positive, which is good. That's what we need to be inside a log. So there's nothing wrong with that value, and we can say confidently that that is our answer. E. Let's say that I had something like log base 3 of x and everything here squared minus log base 3 of x cubed plus 2 is equal to 0. Now, the very first thing that you should note here is this square. You might think that you could throw that to the front, all right, because it's an exponent. You cannot. You cannot move that to the front. The power rule does not apply there. How come? Because in here, this square is squaring the log. It is not squaring the argument. It's not squaring the x. This 3, however, that one you can move to the front because that is squaring the x. So, it's cubing the x. So this is an actual power to the argument, which makes it that you can put that to the front. This right here is not a power to the argument of log, though, which is why you cannot move it to the front. So in here, we're going to write this as log base 3 of x squared minus 3 log base 3 of x plus 2 is equal to 0, and that right there is a base 3. At this point, we're going to do a substitution. We're going to do a u substitution. All right, so I'm going to say let u be equal to log base 3 of x. So this right here is going to tell me now that we have u squared minus 3u plus 2 is equal to 0. And that we know how to solve. This is factorable. This is just u minus 2 times u minus 1, which gives us that u is either equal to 2 or u is equal to 1, right? And then we say, well, the problem was not about u. It was about your x, all right? So you had to put things back into terms of this x over here, all right? So we're going to say, well, this is really just saying log base 3 of x is equal to 2 or log base 3 of x is equal to 1, which tells us that x is equal to 3 squared, in other words, 9, and that's an x. Or x is equal to 3 to the 1, which is just 3. And those both work, all right? Those both work. How come? Because from the very beginning, in here, the domain was x must be greater than 0. In here, it was x cubed must be greater than 0. But that's equivalent to you saying that x must be greater than 0. So both of these answers are greater than 0. We're good. All right, so that was E. F. Let's do this. So let's say that I have log base 7 of x plus log base x of 7 is equal to 2. All right, we're going to start simple here. Well, how do we start this? notice that as written, we cannot combine those. All right. Now, why can we not combine those? The reason we can't combine those is because, well, they're not the same base. I've got base 7 and base x. Perhaps if I made them look more like 7s and x's, they would look way more different. So this one was log base 7. This one was log base x. There we go. So since they're not the same base, we need to come up with a way of combining these somehow, because we need to have just one log on each side at most. Well, let's see. The very first thing I'm going to do here is I'm going to remind you of the change of base formula. So log base a of b is ln of b over ln of a. Technically with any base, but I want you to remember it with natural logs. I want you to know how to apply it with that. So what we're going to say is this line right now becomes ln of x over ln of 7 plus ln of 7 over ln of x is equal to 2. The next thing I'm going to do here is I'm going to multiply the entire equation by the common denominator. And the common denominator would be ln of 7 times ln of x. All right? So ln of 7 times ln of x. And I'm going to multiply that on both sides. In the first term, well, the ln of 7's cancel out, and I end up with ln of x times ln of x, which gives me ln of x quantity squared. Plus, in the second one, the ln of x is canceled out, so I end up with just ln of 7 times ln of 2. And on the right side, I end up with 2 ln of 7 times ln of x. All right. Now, at that point, I'm going to put everything to the same side. So I'm going to write this now as ln of x quantity squared minus 2 ln of 7 times ln of x plus ln of 7 times ln of 2 is equal to 0. Right? And, well, what that's going to give us is, oh, wait, hold on. I just realized this right here is all messed up. Look at that. That's awful. In here, the ln of x is canceled out, so ln of 7 times ln of 7 would have given us ln of 7 squared. Look at that. Let's fix that over here too. Ln of 7 squared. There we go. All right, now, what I want you to notice here is that we have a form here of, let's do it this way, a squared minus 2ba plus b squared, right, where a is ln of x and b is ln of 7. Why do I want you to notice that? Is because, well, we can factor that. But let's see how we will factor it. This right here, I'm going to do a u substitution. So I'm going to say let u be equal to ln of x. So this becomes simply u squared minus 2 ln of 7u plus, well, actually, you know what? Let's do it this way. And I'm going to say also let a be equal to ln of 7. Just so that we can rewrite it this way. U squared minus 2 AU plus a squared is equal to 0. This right here would factor out to be u minus a squared is equal to 0, right? And then in here, taking the square roots of both sides, I end up with u minus a is equal to 0, so u is equal to a. But what was u and what was a? Because we know the problem wasn't about u, right? The problem's never about u. The problem has to be, it's always with your x over here. So what we need to do here is just write it as ln of x is equal to ln of 7. And I should be writing it right now. Ln of x is equal to ln of 7, which gives us our final answer of x equals 7. All right. And let's see if that makes sense. Let's plug it into the original question. So if I had 7 here and 7 here, so I have log base 7 of 7, which is 1, plus log base 7 of 7, which is also 1. So 1 plus 1 is 2. Very, very exciting. So that's definitely the right answer there. All right. Let's do one more and then we'll call it. So that was F. G. And this, right, here's G, right? That was F. Yeah, G. So let's say that I had something like log base 16 of x plus log base 4 of x plus log base 2 of x is equal to 7. So what do we do? Right? Because again, we have a problem where we have very, very different bases in all of these. Well, what we're going to do is apply the change of base formula all over. So what we're going to do here is this, applying the change of base formula, ln of x over ln of 16. This, applying the change of base, ln of x over ln of 4. And this one, ln of x over ln of 2. And that's going to be just simply equal to 7. Now, 16 is 2 to the 4th. 4 is 2 squared. And why do I care about that? Because, well, ln of 16, which would be ln of 2 to the 4th, would simply just be 4 ln of 2. Similarly, ln of 4, which would just be ln of 2 squared, would simply be 2 ln of 2. So let's write that. So I have ln of x, and let's go ahead and write in white again. So I have ln of x over 4 ln of 2 plus ln of x over 2 ln of 2 plus ln of x over ln of 2 is equal to 7. At that point, I'm just going to multiply by the common denominator. And what's the common denominator? 4 ln of 2. So I'm going to multiply both sides here by 4 ln of 2. And what that does for us, well, on the left side, 4 ln of 2 times 4 ln of 2, that cancels out, so I just end up with ln of x plus 4 ln of 2 with this 2 ln of 2 become just 2, so I have 2 ln of x. And over here, this ln of 2 cancels out with the ln of 2, so I'm just left with 4 ln of x is equal to 7 times 4 is 28 ln of 2. So in here, simply what this says is 7 times ln of x is equal to 28 ln of 2, which is simply saying that ln of x is equal to 4 ln of 2. From the power rule, I can rewrite this as ln of 2 to the 4th. So x is simply equal to 16. All right. Now I'm going to call it, I'm going to say that this is the end of 3.4. But there's obviously a plethora of more other examples that exist out there. But if you noticed, every single problem used one of these properties at least. Where are they? At the very beginning. Every single problem used one of these 3 properties. Well as I guess I should add it here now. The change of base formula, which again was log base a of b is equal to ln of b over ln of a. All right. But every single one of them use these properties. So it's all about manipulating the problems to use these properties so that you have something nice to work with. All right. So that is the end of 3.4.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.